All right, so I'm Robert Heath. This is Wireless Communications Lab, lecture number 26. All right, so today we're going to cover a couple of topics. One, we're going to talk about the performance analysis of spatial multiplexing and fading channels. We started this in the previous lecture, but we'll finish it today. And the key difference here between this and what we covered in the earlier part of the lecture last time is that we have fading in the channel now. So before we were conditioning on the channel, now we're going to get rid of that conditioning and take the expectation. And the second topic we'll talk about is channel estimation for spatial multiplexing. And so here we're going to look at what you need to do to estimate all those channel coefficients. So I'll explain, the different ways of doing MIMO channel estimation. So you should be able to articulate how you estimate the channel and then construct at least one simple channel estimator using orthogonality. But we'll talk about a few different channel estimators. And then this is what we're going to do today. If we have time, we'll also talk about MIMO OFDM. All right, so first, just a quick review of the spatial multiplexing vector symbol error rate. So this is the expression that we derived last time in class here. There, sneeze again, maybe. Let's see. All right. So this is probability of error condition on the channel here. And then this is the union upper bound as we've been doing before. This is the number of vector symbols right here. This is the distance between two vector symbols squared over 2. This is ES over N naught, and this is NT because we're splitting power among all the symbols and all the antennas here. Now, one thing I wanted to point out is we could, last time I left the expression essentially like in this form here, but we can define a new notion of minimum distance. But that notion of minimum distance corresponds to the minimum of this quantity here, h s of k minus s of l, where recall that sk and sl are two different vector symbols. And so minimum distance for spatial multiplexing is a function of the channel. And this was different than we saw in the, single antenna case. Is different than we saw with maximum ratio combining, different than we saw with the Alamuti scheme. And it's one of the ways that using MIMO communication is fundamentally different than those other simpler transmission techniques. That there's a different coupling between the symbols and the resulting error performance. This has a lot of implications to me. One being that it's hard to predict error performance because you have to know how these particular vectors here interact with this matrix channel. And so you have to have some, understanding of that. And, the larger the set of vectors you use here, the more vector possible errors you have, but you still have to understand how they interact with the subspace structure of the channel here. So anyways, the performance ends up being quite different here. So now what we want to do is we want to get rid of this expectation. So we want to take the expectation of this Q function here and get rid of the channel. And we're going to do that now using similar tricks as we did before here. So here, I'm going to go through this derivation, and it's going to use a couple different properties from matrix theory that you may or may not have seen before. And essentially, the objective is to get this in a similar form as what we've used in other similar derivations. So we're going to exploit the properties of the complex Gaussian vector distribution and the integral of that distribution going to 1. So it's going to be, at some point, proceed very similar to what we've done before. We just have to get it in that form. Now, so what I'm going to do here, first off, is I thought I would save myself some time here and review some vector and matrix properties here. All right. Trying not to drip on my notes here. That would be bad. So, first thing I wanted to introduce is this concept called the Kronecker Product. You may not have seen it in, the undergraduate linear algebra course. The Kronecker Product is written like this: is A, usually this star with a circle B. And what it is it's this Kronecker Product defines a new matrix. And that new matrix is constructed by taking the second matrix here, the B, and replicating it. And each replica is multiplied by a coefficient in the entry of A here. So, I mean, it may seem strange, but this has, various applications here. And then just as an example, if you're ever taking the Kronecker Product between these two 2x2 matrices, first of all, by counting up the number of B's here, you can see that the dimension should be the products of the dimensions, products of columns by products of rows. So this would be 4 by 4. And then you can see that the first entry here is going to be 1 times B. So it's going to be 1 times 0, 1 times 6, 1 times 5, 1 times 7. So this is kind of like the first B here. This is like 3 times B. This is 2 times B. And this is 4 times B here. So anyways, that's the Kronecker Product definition here. Now, Kronecker products come up when we use this other operation that I also mentioned last week, or last lecture, on called vectorization here. And so the vectorization is written as like VEC or VEC of a matrix A here. So I had like a matrix A, B, C, D. I'm going to stack the columns on top of each other and create AC, BD here. So vectorization is basically a stacking of a matrix into a vector. And this is going to be useful, and actually it comes up in a lot of places because, we have distributions defined more easily for vectors than matrices. We have optimizations maybe defined more easily for vectors than matrices. So a lot of times it's used to convert some problem that's a function of a matrix into a vector. Now, the main property that we're going to use, which is why I'm introducing the Kronecker product, is this property that if you have a product of 3 matrices, A, B, and C, and you vectorize that product, it can be shown that, with some algebra, that this is equal to the Kronecker product of C transpose and A times the vec of B here. And so this property actually is used in several places in MIMO communication. It's used for this derivation that I'm going to show you. You can also use it for channel estimation. It's generally useful any place where you want to convert a product of a bunch of matrices into a vector. And what it does is it allows you to pull out one of these vectors here, in this particular case, this B here, in vector form. So for example, if B was like our unknown, that would go here, and then you could have, the known stuff over here. That's how we would use it for channel estimation. All right, so that's the Kronecker product here. So now let's go and look at the derivation of the probability of error here. I don't really think I'm sick, as my sweater has some dust in it, so I shouldn't have taken it off. Or alternatively, I should occasionally wash my sweater, which I guess also work. Glad we're getting this on video. Good. So what we want to do is we want to compute the expectation of the probability of this ES over N naught given this matrix channel H, which is upper bounded by this quantity here, times the expectation of this Q function that we had in the previous slide. Something like this here. So now what we're going to do is we're going to focus on the deriving the expectation of this quantity here. And we're going to use the same trick as before, which is the Chernoff upper bound. So we're going to focus on looking at the expectation of e to the minus. So we take the argument here. Remember, we square that argument and divide by 2. So we're going to get the expectation of EX over, I'm going to actually put the, N naught, NT, and then H, S of K minus S of L, magnitude squared, over 4. Okay, so the trick now is really just to simplify this here so that it looks like something that we can deal with here. Now, what we want to do is we want to get H in vector form instead of matrix form because we know and have already used the complex Gaussian multivariate distribution, which corresponds to a vector. Writing distributions for matrices is more complicated, so if we can get this in the vector form, we can avoid that complication. So first of all, let me put this here. So just note that if I vectorize this channel here, then it's going to be complex Gaussian with zero mean, identity covariance of dimension NT NR by NT NR here. So this is what I know here. So I'm going to try to now get this whole thing in vector form here. So what I'm going to do is I'm going to define, well actually, okay, there's different ways to do this here. Yeah, let me define E of K comma L as equal to the difference between S of K and S of L. This E is an error vector. It's the difference between two vector symbols. And now I am going to vectorize this quantity here, H, E, K, comma, L. Now, I have a product of two quantities here. Now, if you go back and look at our vector identity here, you see that we have three matrices here. But we can always multiply either side by an identity. So the question is going to be, do we treat this as identity HE or HE identity? Well, since we want to pull out H, we want H to play the role of B to be in the middle here. So we want to put an identity over here. So I'm going to write that out just for completeness here as the vec of an identity matrix times H times E to the K comma L. And now I'm going to plug in my Kronecker product formula here. So B is going to be, so this is going to be C transpose. This will be E K comma L transpose. Kronecker product with identity times the vec of this H here. Yeah, really should wash my sweater at some point. All right. Maybe 2014 I'll wash it. So, what I want to do now is I want to connect this back to this here. So, let's see, how do we do that in an obvious way here? All right, so using this Kronecker product identity here, this thing right here, I can look at the norm of this quantity, which is going to be E of k comma L t, Kronecker product with identity times this vector of h here. And if you go through and look at this quantity here, so first of all, we have to look at what does this look like. So this right here is going to take, so remember we go back to the Kronecker product here. We're going to take the first entry, multiply it by the second, and so on here. And so that gives us here, hold on a second here, to do this correctly here. No, it looks okay. Yeah, I'm just trying to see the, yeah, so this will be essentially like this E of the first entry here of like E1, K comma L. And so on, down to E of NT of K comma L times the identity. And then this whole thing here would be multiplied by, this is like the first row of H, this is the second row of H down through H of NT here. And so if we go through here and you look at each of these different sums here, so what we're going to get here is we get, if I multiply this out, this is an identity matrix, so I get that this is equal to E1 K comma L times H1 vector plus E2 K comma L times vector H2 plus dot 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 plus E of K comma L NT vector of NT here. But this quantity here, right, this is actually just equal to, this is just H times E of K comma L. So I just wanted to go through and show this to you because I actually don't need the norms here. But basically, this quantity here is equal to this quantity here. And so now I'm going to expand that. So that's the main point of this here. These guys are both equal. And this seems like much uglier than this one, right? But when we expand it, this is a matrix times a vector. So the norm of that squared is going to be equal to the vec of this matrix conjugate transpose times this thing here, conjugate transpose. So we're going to get E, we'll put here a conjugate, K comma L, Kronecker identity, times and yeah, I forgot to tell you the properties of the transpose of the Kronecker products, the transpose of the entries in the Kronecker product. And E comma L, K comma L transpose, Kronecker identity here times the vec of this H. Now I need to use one more product I forgot to tell you about here, which is that when you multiply two Kronecker products together, if, essentially the dimensions here are conformable, then this is equal to the Kronecker product of the separate products here. So this will be equal to the Kronecker product of E conjugate k comma L times E k comma L transpose, Kronecker product with an even fatter identity matrix here, times vec of H here. Actually, identity is the same size there. Yeah. So this right here, I have the conjugate and the transpose here. That's actually it's not that important, it turns out. But basically, this right here is a tall vector, times a fat vector. So that's like a matrix. It's a rank 1 matrix here. We're going to call that we're going to call that. Sorry, what's that? Yeah. So we're going to call this thing here a matrix. We're going to call it R of k comma L. So then this whole thing here we're going to rewrite as the vec of this H times R k comma L Kronecker identity vec of H here. Now this RK here is what we're going to call the error covariance matrix. If you study space-time coding and other kinds of MIMO transmission strategies, you'll deal with this quantity here in more detail. So essentially, what we've done is we've rewritten this, we've basically rewritten this quantity here as this product here. And now we're going to go back and substitute that in to our expectation. And so we're going to write expectation of e to the minus ex over n naught times nt times this h s of k minus s of l square root over 4 is equal to the expectation e to the minus ex over n naught nt vec of h star r k comma L Kronecker identity vec of h divided by 4, and I'll just put the 4 over here. Now, what we do, believe it or not, is we just plug in the fact that we know that this vector of this channel is complex Gaussian with zero mean identity covariance here. So this looks basically at this point just like the MRC derivation, almost just like the MRC derivation. This is going to be some, multi-dimensional integral over e to the minus ex over n naught nt times 4 vec h star r of k comma L Kronecker identity vec of h times 1 over pi to the, this is ntnr by ntnr, so it's going to be pi to the ntnr times e to the minus vec of h star vec of h here. Because this right here is the distribution that corresponds to this up here. And all I've done is put the vec in there instead of just writing this as h. Otherwise, this is more or less like the MRC kind of derivation that we did. With the exception here that we have a matrix here that we have to deal with. So we do kind of the same trick we did before here. We rewrite this whole thing. We're going to put the pi to the ntnr here. I'm going to leave a gap here. I'm going to rewrite this as e to the minus ex over n naught nt times 4 vec of H star. So here we have an identity. Here we have this quantity here. So we're going to have R of K comma L, Kronecker identity, plus another identity matrix times the vec of H here. And we remember that if this distribution here had a covariance, that covariance would be here in the inverse here. So this is effectively the inverse of a covariance matrix, and so we're going to put the determinant of that matrix here in the numerator and denominator, which we didn't leave enough space to write neatly. Let's write it really small. Identity inverse, because this is the inverse here, should be the inverse. And then same steps as before. Sorry, this thing, we have the dH11 through dH of NT and R here. Same steps as before, that this whole thing here integrates out to 1. And so we're left with 1 over, so we're left with the determinant of this inverse, which if it's, is actually the inverse of the determinant. And that's equal to, oh, sorry, I forgot I had made one small mistake here, which is that this actually has to be over here. Sorry, that should be there. That should be over there too. So we end up with EX over N naught NT times 4. Actually, we should have an 8 here. Where did I go? 4. Sorry, yeah. Sorry, actually, that should have been 8. Because it's 2 squared times 2. So we end up with this, odd-looking quantity here. What's that?
Why that got cancelled?
Because the multivariate Gaussian distribution integrates to 1, just like in the MRC case, just like in the scalar case. So, because this is the distribution function here. So it's the same trick that we used before here. And we integrate to 1 because I put the, this is a covariance matrix, the inverse of a covariance matrix. I put that here in the denominator, and then I put it also in the numerator. And so all of this canceled out except for that. And that's what this is here. And the only thing is I forgot to put this scalar inside there. And so now here, yeah, let me see here. Simplification. Right, okay. So, yeah, I'm forgetting one other property of the Kronecker product here, but essentially, if you look at this right here, what this is all right, it's not that obvious here, but basically, it turns out that this thing here is equal to EX over N naught NT times 8 times R K comma L plus identity here to the power of NR. Because that's the dimension of this here. I'm using a property which I didn't prove of the determinant of the Kronecker product of a matrix with an identity is equal to the determinant raised to the power of NR. This actually is a more complicated eigenvalue relationship, which I'm skipping. But anyways, the net of this is that this here is equal to this quantity here raised to the value of nr. And now I can use, yeah, I forgot how many matrix properties there were in this derivation here. I can use this property that if I have the determinant of I plus AB, that's equal to the determinant of I plus BA. And so I write this out. Remember this RK here was E conjugate times E transpose of K comma L. So this is actually equal to 1 over, and this is an outer product, so that becomes an inner product. So this becomes 1 over EX over N naught, NT times 8, the norm of E of K comma L squared plus 1 raised to the NR here. That's actually the final result, believe it or not, that we wanted to get here. So let me now write this in, let me kind of summarize the result here. So basically, what we've done here is we've shown that probability of error is less than or equal to So this is effectively what we've shown here. So we see a couple interesting things here. First of all, that, this is kind of the usual stuff we expect here. We see here we have an NR here. So what can we conclude about the diversity? Here, what is the diversity order here? Is NR. We saw this exactly with maximum ratio combining. Now, you have to remember, though, that there's actually NT times NR dimensions. So you might expect that there's NT times NR here, but indeed it only turns out to be NR. You can get NT by NR by doing some coding over time. But without that coding, you get only NR order diversity. The second thing is that here what we care about is, in terms of the SNR gain, is this magnitude squared of this error vector here. Well, what we care about is the worst error. The worst error is going to be the one that's here is the smallest. And so the smallest here, right, if I minimize over all possible error vectors this quantity, right, remember that this quantity here is just the sum of the entries it's the sum of each individual error squared. And this, the worst case here is where all of these are the same, and one of these equals the d-min of the component constellation. So this minimum here is actually equal to d-min squared, and I'll put kind of a C here just so you remember that this is the d-min of the constellation C here. And this is different because in the case of if we go back over here, when we looked at the Gaussian case, the error performance was a function of the channel. Here it's not a function of the channel, which makes sense because we took the expectation. So it can't be a function of the channel. But here, the error performance was a function of the minimum distance of this channel times the error vector here. And here, the error performance is just a function of the minimum distance of the constellation. So this is, in at least sense, a little bit simpler. And we get the NR here. We don't get the NT. So that's the main result that we're after here. So the main conclusion here is that we achieve NR order diversity. Now there's something a little bit weird about this too if you think about it, because what if you had like 100 transmit and 100 receive antennas? You get 100th order diversity. So it's sort of weird that you get to send more symbols at the same time and decode them more reliably. I don't know, I found that weird. But that's actually what happens here. Now keep in mind that the complexity in that case would grow much higher, right? Because you're searching over, the size of the constellation raised to the 100 power. So your decoding complexity is decreasing exponentially in the length. So you don't get that for free. Now, a couple notes here. So first of all, with a best space-time code, so this is doing something more than spatial multiplexing, more than the Alamuti code. You can get NT times NR order diversity. Now, most of these codes have even higher decoding complexity, and the only one that has seen much use is what's called the golden code. And that was used in, I believe that, I don't remember if it was mandatory, it was part of one of the 802.16e space-time coding techniques there. So it's a way of doing, sending more symbols at the same time over time so that you get a higher order diversity. And then the second thing is that, so we did this whole derivation here for the maximum likelihood receiver. If you use a zero forcing receiver, we will not prove that here, you can show that you can get NR minus NT plus 1 order diversity. And why that's interesting is that, look at this here. This is NR minus NT here plus 1. So this is basically the penalty here, which is NT minus 1, right? So this is NR minus NT minus 1 here. And why there's a penalty is that with zero forcing, you use those different observations to separate out the transmitted symbols. So by doing that operation, you're in effect taking degrees of freedom and using them to help the decoding. And when you do that, you lose them for the diversity. That's kind of the intuition of it. So you can use the lower complexity receiver, but then your error performance isn't as good here. And we don't prove this here, but this is basically this, and this thing here are useful facts to know about MIMO systems here. All right, any questions about this here, this derivation or the conclusion? Yes?
This is the union bound, and in the union bound we are getting the diversity order of NR. So how can, how tight is this, can we also conclude that?
Yeah, it's a totally fair point because we're deriving an upper bound, but it turns out that the tail probability is tight in the sense that the slope is the same. And there's a gap there.
Because even here it shows that increasing NT is actually making the right-hand side worse.
Right, that's right.
Yeah, because even the denominator EX by not
Yep.
NT is decreasing, and even in the numerator it's C to the power NT. So
Yeah. No, that's true. That's true. So I mean, if you were to plot this out, I mean, the highest in our performance, the slope would be better, but the lowest in our performance would be worse. So it would be kind of like you would have, I mean, first of all, this is the union bound. You're right here. But if you plot the actual system, it might look something like that. So that there's sort of a region where having less diversity, smaller numbers of antennas maybe makes sense. And then it kicks in at larger numbers of antennas. I actually don't know, though. I mean, we have to simulate that. I don't know how big that gap is. It may be very small, actually.
It may be because of the decreased transmit power of each antenna. That's the more, like, what's the intuition behind more and more transmit antennas?
Well, this is also, I mean, there's two separate things here. There's the transmit antennas and there's the receive antennas. So first of all, this works if I have one receive antenna and a whole bunch of transmit antennas. Right? It actually does work, and that's just kind of like decoding a very high-order constellation. So the intuition here in that case is that you're using your antennas. Like if I send, say, 2 4-QAM at the same time, I could have one antenna and send a 16-QAM, or I could send 2 4-QAM. And so what happens is the channel kind of randomizes and creates a funny-looking 16-point constellation that maybe doesn't work quite as well as 16-QAM because its minimum distance can be very close together. And then, yeah, increasing NR, if you leave the numbers of antennas fixed, gives you more observations of everything, so you get more noise resilience here. But increasing both NT and NR, I mean, yeah, the main penalty here you get is from this right here. But we also have to remember that this is actually the biggest part of the union bound as we sum over all of these error events. And so this is the piece that makes the union bound looser. I mean, they're both approximations, but this right here is the piece that really kills us here. And that's the piece that actually doesn't really grow with NT. So I think that's the misleading part of what you're asking. So we have a lot more detail on this in my space-time coding class, which you all are encouraged to take in the spring semester here. It'd be just like the wireless lab, except there's no lab and there's a lot more matrices, matrix theory, SVDs. So in other words, it's like twice the fun and half the work. Or wait, twice the fun and twice the work, maybe. Anyways. Other questions about this here? Yes.
We have been deriving these bounds by only considering small scale fading. Like we have never been considering large scale fading while deriving the bounds. How can we assure that it will not make any difference? We have like only been considering the Rayleigh fading or
Right. Yeah. I mean, it's a good point here. Conventionally, the reason that we average over the small scale fading is that if you think about how you're using the phone, let's say a mobile device, there's some coupling between the time scales of these two fading operations, right? This large scale fading, you can also think about it as long-term fading, right? Large scale fading coming from going behind an obstruction, being in front of an obstruction. Think about, you're walking like behind a building. You're kind of behind the building for a long time. And in the world of wireless, where we're sending maybe 1 million symbols a second, that's an eternity. So to average over the large scale fading, you can do that. People have done that. It's tabulated in books. But the intuition, to me, is kind of different because it's kind of like you're communicating and sending information on average over a very, very long period of time. And then, if it's that long, I'm not sure that average is meaningful. But this is meaningful here, the Rayleigh fading, because you get these different fades when you move a coherence distance, which can be this far. So as you're just like, fidgeting around, you're hitting all these different fades. And so somehow this average makes sense to me. But I mean, this is, connecting the theory and the real world. Now, there's another line of thought here, which is that actually these calculations aren't that meaningful anyway because we're only looking at a piece of the problem. There's frequency diversity, there's time diversity, and these are all used in systems as we already talked about. And so even if I use like a linear receiver here, and I get very poor spatial diversity performance, I still may be coding and interleaving over frequency and time, and so I still may get a lot of diversity. So the fact that this diversity performance is much worse doesn't mean that in a real system it's going to be that much worse. In the real system, the performance gap won't be huge. It actually would be very small because there's all these other forms of diversity. But those are that's like a lot harder to analyze. And one of the other reasons that we do this calculation here is that it turns out that this calculation gives us a criterion that we can use later to design space-time codes. So it's just another benefit of it here. Yeah, other questions here? All right, so let's take a short break here. Short break. All right, now this one here, I got super lucky today. This is great, I have to say. This is, so I found this on BBC News. And yeah, so when patents are filed, depending on the country, the patent filings become public domain. So you can actually, you can go to the U.S. patent website and look up filed patents and look up their claims. And so a lot of these articles that come out, these different news organizations are based on patents that are filed, not necessarily products that are being made. But anyways, this product here, Sony has filed a patent for a smart wig. I guess if this was Apple, this would be called iWig. And so this is funny because this more or less reads, the description of this reads like a patent. It says that the smart wig can be worn in addition to natural hair and will be able to process data and communicate wirelessly with other devices. So that's the wireless piece right there. See? It makes sense, right? You don't want to wire up your smart hair with your phone. That would be silly. According to the filing, the smart wig can help navigate roads and collect information such as blood pressure. And then, this is blah, blah, blah about wearable gadgets here. Oh, yeah, and this is more details about the patent filing. So if you've ever filed a patent or read a patent, you'll recognize this here. The Japanese firm said the wig could be made from horse hair, human hair, wool, feathers, yak hair, buffalo hair, or any kind of synthetic material. This is in a patent, when at some point you try to make it as specific as possible to show that you're kind of aware of how it's going to be implemented, and that gives the patent more credibility. At the same time, you don't want someone else to come along with something that you haven't thought of, and then they claim that, oh, that wasn't in the patent. I'm going to use yak hair. Obviously, they didn't think about yak hair, and therefore this patent doesn't cover it, right? So they enumerated, I guess, whatever materials wigs are made of nowadays, which I'm kind of surprised that yak hair is here, I have to say. Horse hair I knew about. Huh. Anyways, yeah. And then, oh yeah, the communication interface and sensors placed in the wig area are at least partly covered by parts of the wig in order to be hidden from sight during use. That is interesting here. Right, so I can see this now, in one embodiment. The communication interface and sensors are partially obscured, in another embodiment. The wig is made from yak hair, etc. here. Oh yeah, let me see here. This actually keeps going on here. The usage of a wig has several advantages that, compared to known wearable computing devices, include a significantly increased user comfort and an improved handling of the wearable computing device. That seems arguable to me. See, helping blind people navigate. Yeah, I mean, it is said that a small video camera or sensor in the wig could help provide the position and location of the wearer. Yeah. A remote user can use images provided and send vibration commands through the network and navigate the wig user manually to a desired destination. That's kind of like the cockroach concept here. Interesting. Oh, and a further improvement could be the wig may use ultrasound waves to detect objects around a user. Anyways, yeah, smart wigs. Any comments on this here? I guess first the obvious case here, how many of the men here in the audience would be interested in wearing a smart wig? Yeah. I mean, I could see like, sport-themed baseball caps or something, but I don't know. What do you do if you have basically no hair and then you want to... Yeah, that seems extremely odd too. I suppose a smart toupee would be a derivative of the smart wig. Any other comments on this here? Yeah. Except you probably wouldn't want it in these gaudy colors here. Something a little more natural looking, like, like the yak hair, for example.
How long does the battery last?
Well, it's a patent, so it doesn't say how long the battery lasts. These are just like, graphical illustrations probably pulled from Google Image. Probably has nothing to do with what's in the patent. But yeah, that would be of course, a whole set of problems, right? How do you attach the wig? How do you charge the wig? It's surrounding your head, which is where they do all this electromagnetic testing. So presumably you couldn't use very high power wireless stuff there. So then how does it connect to your phone? Does it connect with Bluetooth? I mean, there's, a whole bunch of interesting research problems here. I mean, you've also got the human-computer interaction thing here, because they're talking about the wig vibrating and giving information. But so how else could it convey information to you? There's a lot of ways. I mean, it could be like tapping. Like it could be like tapping code in the back of your head, for example. It could be whispering in your ear. You could have a little mic there, little mic or a little speaker. Yeah, I mean, that's a lot of possibilities here. Well, these are companies with a lot of money, and so, they want to patent stuff. I mean, the thing with patenting is it requires an element of seeing the future, because first of all, a patent can take a year or up to, like, say, even 8 years to issue, and then it's good for 20 years. So you're coming up with something, and, you really have no idea in 10 or 20 years if this is something that will be useful or not, Because if it was, you'd file 500 patents on it. But so you can just sort of like file a few here and there and see, some of them will be useful, some of them will not be. But yeah, I mean, it's like a lot of wireless opportunity here. I don't know. It just seems, I'm just trying to get around I can't see wearing a smart wig. I can see wearing the Google glasses or even the smart watch, but the wig is just, I don't know. I'm just not getting into the wig. Yeah, no more comments on this here?
Well, I guess from a MIMO perspective, maybe they should take that with each one of the hair strands. Just an antenna.
Yeah.
Get some beautiful diversity right there.
That's right. That's right. Yeah, I mean, there's all kinds of ways that you could integrate the technology with this. So.
Well, then I guess also energy harvesting.
Yep.
Wind blow by the hair, and every time the hair strands flex, you might be able to get enough energy out of them.
Yep.
10,000.
Yep, energy harvesting. Yep. Or it could just be harvesting light energy too, right?
Yeah.
You could make little tiny solar hairs. We should be patenting all of this here.
Yeah.
Yeah. All right. So, let's see, what else do we have here? All right, now we move from wireless wigs down to something slightly more concrete, channel estimation for spatial multiplexing here. So the use of multiple antennas changes, almost everything we've talked about in the class. I mean, you can play tricks to use all the techniques we've talked about, but there's a whole host of potentially smarter ones available to you. So I'm going to talk about one of the impairments that we focus on quite a bit, which is channel estimation. And so I'm going to talk about how you can do channel estimation, at least in a simplistic way. in MIMO systems here. So you should be able to explain that principle and construct at least one channel estimator. And then I'll also, if we have time, I'll draw a block diagram of the whole system so you get a sense of how it looks, including the pulse shaping, et cetera here. All right, so let's go. I think we're on 6 here. All right, so channel estimation. And this concept here applies just generally to using multiple antennas, not necessarily just spatial multiplexing. Anywhere you want to use multiple transmit and receive antennas. Now we're going to focus on the flat fading case for now. And the idea is that we have this matrix channel where there's all these coefficients here, h of k comma L here. Right, we have this matrix channel H, which has the coefficients in it. Going this way and that here. Okay, so now what we want to do is we need H because we need it to either do the ML detection or the zero forcing or whatever other receiver we might implement here. So how can we how can we estimate the channel here is the game here. So, look up here, make sure I don't lose my place here. Yeah. Okay, so estimate H using known training sequence or sequences here. Okay, so there's a couple of ways to do this here. So first of all, we'll start off with maybe the simplest approach. Now keep in mind here that, so let's consider, just as an example, we'll look at spatial multiplexing here. If we're using spatial multiplexing, the input-output relationship looks like this here. And so the general situation here would be to send a whole bunch of training vectors and use those vectors to estimate the H. We'll do that in a minute here, but I want to start with something that's a little bit simpler here. So the thing is that we need to send training data on each of these antennas. Now, a very simple approach is to use, is to train each antenna separately here. So the idea is that we're going to send, let's say, training symbols on the first antenna. I'm going to use M to denote the length of the training since I abused NT and now use it for the number of antennas here. So supposing that this is like my first antenna, let's say. And then, whoops, sorry, I gotta actually put this over here. And so I'm going to train on the first antenna, and then I'm going to send 0 the rest of that time. And then let's say on the second antenna, I'm going to send nothing, and then I'm going to train that antenna. And then I'm going to send 0, and so on here. So if I do this, effectively what I'm doing is I'm creating a MIMO channel. So basically, I have these multiple transmit antennas where I'm essentially sending 0, I'm sending training from 1, and I'm sending zeros on the other ones here. And so at each receive antenna, what I'm going to do is I'm going to get from here, this is the kth transmit antenna, this is going to be H1 comma K, H of 2 comma K, etc. here. So each receiver, YK of n, will see H1 comma K, T of n, plus VK of n here. And so a very simple approach here would be just to take the received signals from each antenna separately here, stack them into a vector. We could call this like YK is equal to H1 comma K of T plus this VK here. We know using the usual least squares principle that we could then call our least squares estimate H hat of K as, this would be, let's see, T star of T inverse T star Y of K here. And so that's, one very simple form of channel estimation here. So all we did again is we excited just one antenna, and then we just estimated all the channels separately from each of the receive antennas. Now you could group them all together and estimate them at the same time, but it turns out if the noise is uncorrelated, there's no advantage to doing that. So you can actually show that the least squares problem decouples into a bunch of least squares problems. So there's really nothing wrong with this approach here. So this is like one simple channel estimator here. Now the problems here is that it requires turning off antennas, which if you're doing this in like this very simple format here, where we're doing everything with single carrier, it's very difficult to ramp the power down on an antenna and then ramp it back up. Like in GSM, they had those guard periods at the beginning and end to help with the ramp up and ramp down potentially. So you really don't want to have to turn off an antenna and turn it back on. So that's actually not practical. Now, if you're doing an OFDM system, you can actually make this work because you can do things in frequency. But that can be a challenge here. So we're going to look at some other possibilities as well here. So now let's look at something that's slightly smarter here. So now let's consider where we're going to use on each transmit antenna a different training sequence. So training at the same time and so let's say that we suppose that we have, a family of training sequences, TK of n, where k goes from 1 through nt, and n goes from, let's say, 0 through mt minus 1 here. So we have like a family of training there. And so now let's look at the problem again. So if we train each antenna separately here, so we look at the output of the kth antenna, we're going to see that the output at yk of n is equal to h of 1 comma 1 t1 of n plus h of 1 comma 2 t2 of n plus dot 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 plus h1 comma, let's see, nt t of nt of n plus v1 of vk of n here. So at the received signal y here, you see that you have a mixture of all of these different trainings, right? Mixture. Of the symbols here. So, but these unknowns here, look at the unknowns, H11, H12 through H1 of NT. These unknowns don't appear at any other antenna. So if we want to get these unknowns, we need to process this received signal. Since the noise is uncorrelated, we actually don't need to look at the other antennas. So we can still look at just this one antenna. So all we're going to do is we're going to, formulate what looks like a least squares problem again. So let's look at what we know here. We know 0 through mt minus 1. So we're going to stack together and create a vector y of k here. And then looking at this right here, we know that our unknowns are h1, h12, etc. here. So we can write this like this here as h1 comma 1, 1 comma 2, down through h of 1 comma nt. And then I can just fill in here the coefficients here. So this is going to be like t1 of 0, t1 of 1, dot, 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 t1 of mt minus 1, etc. here, going from t to nt, 0 down through t of nt of mt minus 1 here. And of course, we have the noise vector over here. So I can call this right here, let me call this t, call this unknown here h of, what did I do here, h, k, should be k here. H of k, and then we can go through here and write the least squares solution as t star t inverse t star y of k here. And so this is like a slightly, more complicated channel estimator here. Now what I'm going to do is I'm going to write this out in a third way, which also is very common and still leads to kind of the same result here. So what I'm going to do now is I'm going to take all of the received signals together. I'm going to write them as a fat matrix here. Not your phone, huh? So I'm going to make this thing here a fat matrix Y. And then, because of the way I'm writing it here, right, with the observations as columns here, I'm going to put this H here. And then over here, I'm going to put this matrix here, which is just like the transpose of what I just had. Y1 training 1 through T1 of MT minus 1, dot, 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 T, and T of 0, dot, 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 T, NT of MT minus 1, plus noise here. And so then this is a, let's call this T. It's a little different T. It's the transpose of the T that I used earlier here. But then we get this matrix equation, y equals ht plus v. And you can go through here and see that essentially, if I was to take just one row of this, then that would correspond to one row of this H hitting my T matrix. And if I took the transpose of the whole thing, I get exactly what I just had. And so you can show that if I just go through here and I multiply through on the right by T conjugate transpose, take the inverse, I can get that t hat equals y t star t star inverse here. So this is just another way of writing the channel estimation kind of in a stacked up together form here. And this is just equivalent to what we just did in the previous case, but doing it all at once. And then the final point I want to make here, I'm just going to have that much time here, is the role of orthogonality here. So if we have some form of orthogonality, we can get rid of this matrix inverse essentially here. So note that, and we saw, see we have t star here. Over here we had t star t. Basically, if we have, let's say, t bar star equal to identity, right, then what does this mean here? What this means is that this training sequence here, when multiplied by this one here, gives you 0. So this means that the training sequences are orthogonal across the antennas. And if you do that, then h hat is just equal to y t bar star here. And then, so that makes the estimator much easier. And you can show that if you use the orthogonal training, then you also preserve the whiteness of the noise here too, which makes the estimator better. But this is, essentially as simple as you can get here. And so we don't have to have orthogonal training, but orthogonal training makes a lot of sense. And also look at this right here. This is basically just an example of orthogonal training. If I look at this matrix here, I mean, the norm is not 1, but that the norm of it doesn't matter here. So this is orthogonal to this, right? Because this is 0, this is 0. So this is just a special case here. So generally, the training in MIMO we generally send data on all of the antennas, but if possible, we would use some sort of orthogonal sequence here. Now, the tricky part is if you go to a non-flat fading channel. We have frequency selective channel. Well, it becomes a lot more complicated, and we don't use exactly orthogonal sequences because we're going to have to estimate multiple taps of the channel, but you can use sort of a similar principle of using sequences that have low cross correlation, like the ones that are used in GSM for training. Those sequences have low cross correlation, so you could build training using multiple different families of sequences there. So that's more or less it here. I was going to draw out the entire block diagram. I guess I'll do that on Monday next week. So just to conclude here, I mean, so we talked about this problem of channel estimation. So you should be able to explain how we estimate the channel, summarize these different ways we can use separate training all the antennas, processing received signal at once, processing them all at the same time. And then the second thing we did was, the first thing we did was probability of error, the spatial multiplexing and fading channels here. So here, the things to get from this part here is one is, this derivation. I mean, we used a couple of tricky identities there, but more importantly, we got that in a form that we could use a trick that we had applied already based on properties of these distributions. And then based on that result, we found that the maximum likelihood receiver had a diversity order corresponding to the number of receive antennas, irrespectively of the number of transmit antennas. And so that was interesting there. And so also I should point out that that whole derivation that we just did, like in there's a very famous paper in 1998 which got a Best Paper Award that has a much more complicated derivation. So this kind of recognition that you could apply this trick of that simple integration, came several years after that. It wasn't in that initial paper there. And so if you don't do that and you go directly from the complex Gaussian distribution, from the matrix distribution, man, it's a lot more complicated. You have eigenvalues, and it's really messy there. So what I'm showing you is something that's really pristine and clean, and probably isn't simpler than that. Though I realize it was not easy, but it's at least gives you a flavor for how things change in MIMO systems here. All right. The other thing is, so we'll have maybe one more lecture talking about some MIMO concepts next week, and then we're going to have a review. So it would be great if you could email topics that you would like to see reviewed to me. I mean, otherwise I'm just going to talk about various things that we've done in class. But if there's something in particular that you want discussed, please send me an email. The other thing is that I have I'm hosting a conference here in Austin next week, so I don't know if I will have the class on Wednesday or not. I have to look at the schedule. I have a feeling I will not, and so if I don't have it Wednesday, I will shift it to Friday, and I'll send you a time. So probably it's going to be on Friday. Hopefully that's not too much of a problem. So, all right, that's it. Thank you.